Okay, one more video on this expanded infinite square potential, where the potential is asymmetric about x equals 0. Okay, what we'll be doing today is looking at finding the expectation values of this expanded well. Alright. So how we do this is we have to use an integral that we've used many times, and I'll give the general case. Okay, so complex conjugate on the left. And the normal wave function on the right. Okay, now since we're looking for the energy expectation value out of all this, we have to sandwich the Hamiltonian operator in between. Now this operator acts on this wave function. Okay, and what we can do here is we can bring this operator inside this sum. Okay, so what does that look like? That looks like magic. It looks like magic. Looks like this. And this is an eigenvalue problem, which returns the energy times the wave function, which is indeed an eigenvalue equation. And we're going to put this into here and see what we can get out of that. Okay, so we'll bring out all the constants to the front, and I'll say straight away that this complex conjugate of this coefficient returns the coefficient, and we're looking at when n equals m, because when n does not equal m, this is going to return 0. So we were looking for a non-trivial value. So what we get is we get the same constant times itself, which is essentially the norm squared. It's always a positive value, always. And we get the energy as well, as we saw from the eigenvalue equation. We get this. That's not an x. That's an x. We get that, and this returns a 1. So what we're left with, well, actually, just do this. What we're left with is this. Nice. Okay, now let's do an actual example with numbers. We'll look for what we get for the expectation value of the second state, so the first excited state. Before we actually do this integral, we're going to make some predictions another way. Now, we remember from the last video that this equaled a half. Let's find what, there should be an n there. Let's see what the energy is. So, for the general case, it was, it was k squared, h bar squared on 2m. Okay, and we remember that k equals n pi on l for the original well, and we expanded the well to 2l. So when we put that in here, we get n squared, pi squared, and 4l squared. Now we'll look at the case for when n equals 2. That becomes a 4, which cancels with this 4. So, what we're looking for in the end, we're hoping that the expectation value will equal a half. times pi squared h bar squared onto ml squared. Okay, that's what we should find from this integral. And I'll move this up here, and I'll box it. That's what we're looking for. Okay, so let's do this. So piecewise, this integral for the wave function that we found before is non-zero in this region. That's why we have that. Now, what was the normalizing coefficient? It was 1 on L square rooted. That coefficient was 1 on square root 2. These are all complex conjugates, and just returns the normal non-imaginary number, I should say. And then our wave function sine, well, the function pi x on L. Then we have to sandwich in Hamiltonian, which is this magical creature. Oh right, yes, and then the non-complex conjugate, which is this phantasmagorical thing right here. Yes. Okay, we'll bring out all the constants to the front. To the front. You can sit out the front. For ml squared in integral. Okay, and this is still here. And it's the operator that's going to be operating on this function right here. Okay, so we just have to differentiate that twice and then bring all the constants again out the front, which will return some magic. So it's pi squared h bar squared on 4ml cubed, and then the integral, and this function returns the same when it's differentiated twice. So I got the sine squared by x on L dx. Okay, that's not a very good pi. Just gotta fix that. Okay, now this integral is not too hard to do. We just have to use a trig identity as we've done before. So it's half. Now, so the 2 down there does a thing with the mathematically. So 1 minus as a cosine. It's a 2 pi x on L. Yeah. Dx. Okay, it's not too hard to integrate. Pi squared h bar and ml cubed. Swish. Swish. And swish. Sine 2 pi x on L 0 to 2L. Alright. So plugging in the 2L, 0 or zeros of course return nothing. 2L in here, that makes that 0, so what we're left is with here is a 0, sorry, a 2L. Oh, you can see it, already. Left with a 2L. So that equals pi squared h bar squared on 4ml squared, which equals what we were looking for. This is amazing. I am amazed. I am amazed. Oh, I'm so happy. I'm so happy. Okay, I hope you're as happy as I am. So there we go. That's how operator usage occurs, and that was the example for energy. So that was a mathematical representation of measurement of energy on this wave function. Okay, I'll see you later. Well, you'll hear me later. Anyway, bye.